All right, so we are at the end of this section. We have one last example to do. I had tried recording this example and kept having issues with my camera, so I'm trying again, but I've already worked through all of this stuff from my previous recording. That didn't work. So I'm just going to basically talk through how I did this problem. Similar to one of the examples we looked at in section 15 or 14.7, we're looking at a rectangular box in this problem. It says find the dimensions of a rectangular box with largest volume if the surface area is fixed at 64 square centimeters. So the function that we want to maximize is the volume function, x, y, z. And the constraint in this problem is the surface area being equal to 64 square centimeters. 2xy plus 2xz plus 2yz, that's your formula for surface area, equals 64. I can use this as my function g, or I can simplify things a bit by dividing everything by 2, just to make the work a little bit easier. Every little bit helps. So dividing everything by 2 gives me xy plus xz plus yz equals 32. The xy plus xz plus yz is going to be my g of xyz. That's my constraint. That's where g comes from. Using the method of Lagrange multipliers, we know that the gradient of f should equal lambda for some scalar lambda times the gradient of g. And we saw in the previous example, really that just amounts to finding the partials of f with respect to each variable, setting those equal to lambda times the corresponding partials of g with respect to x, y, and z. So we start with those partials. Those are very easy to find with these two functions. Fx is equal to yz, fy equals xz, fz equals xy. Very easy function to take partial derivatives of. Same thing with g. The partials here are fairly easy to find. Remember, this is what we're calling g up here. Gx is equal to y plus z, gy is equal to x plus z, gz is equal to x plus y. Those are pretty easy to come up with. Once we have these, we create a system of equations by setting fx equal to lambda gx and fy equal to lambda gy and so on. That's going to give me yz equals lambda times y plus z, xz equals lambda plus x plus z, lambda times x plus z, and xy is going to equal lambda times x plus y. Okay, now this is a system of equations, system of nonlinear equations, and you have multiple different approaches you could take to solve this thing. One thing you could do is try to isolate the lambda in each one of these so that all of the right-hand sides are equal to lambda, making you able to set any of the left-hand sides equal to each other. That's kind of like what we did in the previous example. I'm going to take a different approach just to mix things up a little bit. I'm going to pick different pairs of equations and subtract them. So starting with this first and second equation, if I were to subtract this equation minus this one, on my left-hand side, I'll get yz minus xz. On my right-hand side, I would actually start by distributing the lambda into both sets of parentheses, giving me lambda y plus lambda z, lambda x plus lambda z, and then the lambda z's will end up canceling out when I subtract. So the right-hand side is going to look like lambda y minus lambda x, which we have here. Okay, now I can do a little factoring on both sides. If I factor a z out of this and a lambda out of this, I'm going to get z times y minus x equals lambda times y minus x. And at this point, we have a couple of possibilities. First of all, consider what would happen if y is equal to x. If y and x are equal to each other, then y minus x, which shows up as a factor on both sides, will equal 0. That causes this equation to say 0 equals 0. That's a possible solution. So it's possible from this that y is equal to x. If y is not equal to x, then that would mean that y minus x is not 0. So I could divide both sides by y minus x, leaving me with z equals lambda. That's the other possible case. One of these two things has to be true. At least one of them has to be true. Okay? If I pick a different pair of equations, say this first equation and this last equation, and do the exact same thing, subtract them, you'll notice because there's some symmetry here, these equations all look very similar to each other. The steps that follow are going to look very, very similar to each other as well. So if you follow the work here, we're going to land on a similar looking conclusion. From this new equation, I'm going to get that either x is equal to z or y is equal to lambda. And then I do the last pair of equations. I subtract the second equation minus the third one, go through similar steps, and you should see, if you follow this, the result will look like y equals z or x equals lambda. Now we have a bunch of ors here, but basically if we consider any of the possible combination of cases here. For example, what if it happens that y is equal to x, x is equal to z, and y is equal to z? Well, in that case, it would follow that x, y, and z are all equal to each other. It's easy to see that. What if z is equal to lambda, y is equal to lambda, and x is equal to lambda? Well, then all three variables equal the same number, and so all three variables are equal to each other. Same conclusion. What if we get some weird combination? What if y is equal to x, y is equal to lambda, and y is equal to z? Well, it doesn't matter that y is equal to lambda, because if y and z are equal, and x and y are equal, then x and z would also be equal because they both equal y, and so we could come to the same conclusion. And if you go through all those different combinations of cases, you'll see that you keep arriving at the exact same solution every time. So, therefore, these three dots, it's a mathematical symbol that means therefore, x, y, and z are all equal to each other. What do I get to do with that? Well, if x, y, and z are equal to each other, then I could go back to my constraint up here and substitute x for all of the y's and z's. And if you notice, what that's going to turn this into is x squared plus x squared plus x squared equals 32. That's what I have right here. Combining like terms, that's 3x squared equals 32. Solving for x, I'm going to get x equals the square root of 32 over 3. Normally, you would write a plus or minus here, but remember that x represents the length of one of the edges of this rectangular box, so it has to be positive in the context of this problem. But if x is equal to root 32 over 3, then y and z would also equal that, because we determined that x, y, and z are all equal to each other. So that means the dimensions of our rectangular box, once again, form a cube. There's something about these cubes that seems to be really preferable. We have root 32 centimeters by root 32 centimeters by root 32 centimeters. That solves the problem, and that wraps up chapter 14 for us.